Morning, everyone. I'm Maurizio Palesi, and I'm very glad to welcome you to this second webinar of the Circle webinar series, which is part of the communication dissemination activities of the QUADRATURE project. So the Circle webinar is a series that is designed to foster knowledge exchange and brings researchers together to discuss on topics in the wide area of quantum computing. And for today's session, we have the pleasure to host Jean-Claude Besse from ETHZ Zurich, who will give a talk entitled Modularity at Various Length Scales in Superconducting Quantum Processors. Before introducing our speaker, I give the floor to Carmen Almudever, who is the coordinator of the QUADRATURE project, who will briefly introduce QUADRATURE.
Okay, yeah, thank you very much, Mauricio, and thank you all for being here today. So as Mauricio just mentioned, I'm Carmen Almudever, and I'm the coordinator of QUADRATURE, which is an European EIC Pathfinder project. So the goal of QUADRATURE is to explore the feasibility of architectures that are composed by several quantum chips in order to scale up quantum computing systems, which, as you know, is one of the main bottlenecks of today's quantum computers. And this is enabled by a network with a dual character that includes a quantum coherent link for transferring quantum information between the different QPUs, or the quantum communication between them, and a wireless classical channel that is used to synchronize these communications between the different chips. And both of them are at cryogenic temperatures. In the QUADRATURE project, we take a full stack approach, meaning that we go from the technology up to the applications or the algorithm. So in order to realize this vision, we have a consortium consisting of 9 partners. More precisely, we have EQUAL1, University of Siegen, and University College Dublin, which are working on the development of the QPUs and the cavity for transferring information between the different quantum processors. Then we have EPFL and Delft University of Technology that work in the fabrication of the transceiver at cryogenic temperatures. Then Technical University of Catalonia, together with Catania, developing the protocols that support that classical communication network. And last but not least, the Barcelona Supercomputing Center and ourselves, Technical University of Valencia, working most of the compilation techniques for performing distributed quantum computing, and also in the algorithms itself and the development of the system. So that's in a nutshell what this project is about. So thank you, Jean-Claude, again for accepting our invitation and giving this talk today. Thank you very much.
Thank you very much, Carmina. I would like to add if you want to have more information about the QUADRATURE project, please visit the website. We have also a LinkedIn page, and so I invite you to follow this page where you will find the news, the achievement, and all the things that we are doing in the project. Now, let me introduce our speaker. Jean-Claude Besse is a senior assistant at ETHZ Zurich, a PSI quantum computing hub. He coordinates the fabrication of large-scale quantum circuits, the development of modular quantum computing nodes for improved yield and scalability, and efforts on quantum optics and communication. During his PhD thesis, he developed a single microwave photon detector based on a high-fidelity gate between itinerant light fields and artificial superconducting atoms. Prior to joining the Quantum Device Lab, he conducted research at Caltech on cavity optomechanics. So thank you again, Jean-Claude, and please you can start.
Yeah, thanks. Thanks a lot for the kind introduction and for having me here. So indeed, what I want to tell you today a bit is about our effort with superconducting circuits to build networks of quantum computing devices. And those might happen at very different length scales. And we have efforts that happen at ETH Zurich in the Quantum Device Lab, which is led by Andreas Wallraff, which is more of the kind of setup that you see below, where the distance can be multiple meters, up to 30 meters in our lab. And you have really distant connections and trying to build a quantum internet if you want. And we have efforts that are sort of at distances that are similar to the wavelengths of the lights that we operate with, where the photons are in the microwave, and so the wavelength is a few millimeters. And we look at placing here, you see, for example, 4 small chiplets or modules, as we call them, together on a carrier and try to see how they interface and can work together to do things that maybe a single monolithic chip wouldn't be able to achieve. And this is something that we realized within the ETH Zurich PSI Quantum Computing Hub, which is about an hour away from Zurich in the canton of Aargau in Switzerland. Before I start going in detail about modularity, maybe a quick recap of the kind of qubits and the kind of devices that we work with. We realize if you want our own artificial atoms, our own qubits, using superconducting circuits. We use superconducting circuits so that there's very little loss, and we can realize electrical circuits that behave in the quantum regime with single level of excitations inside. But before going in a quantum regime, maybe it's nice to remind yourself what can you build as a simple oscillator with electrical components. And the simple case is essentially putting in parallel an inductor L here in this electrical schematic with a capacitor depicted as C. And if you quantize or you look at the energy level of that circuit, you will find that they're equally spaced by the resonance frequency or energy h bar omega that separates the energy level of this cavity being in the vacuum, which we denote as 0, or containing 1 photon as a 1 or 2 photon as a 2, etc., etc. The reason why this is not enough to do quantum computing is that all these levels being equally spaced, if you drive this cavity with coherent fields, what you will prepare is just coherent states of light in this cavity and essentially all Gaussian operations, and you will not be able to realize quantum operations. So what you need is some kind of nonlinearity, a way to change the spacing between the 0 to 1 and the 1 to 2 transition. This is mainly realized by adding novel element, a Josephson junction, which we depict at this cross. And it acts essentially as a nonlinear inductor. What we use in our lab is a Tran-Mon qubit, typically, where this nonlinearity is relatively weak, but it's still sufficient so that the first transition, h bar omega, differs from the second transition by a value that we call the anomalisticity alpha in our system. And then frequency selectivity allows you to essentially drive any transition that you like selectively and prepare true quantum states of this circuit, which, for example, might be a single photon Fock state 1. And in that case, because it's nonlinear, we don't typically talk about photons, but we say it's the first excited state of our qubit. This Josephson junction, it's actually 2 islands of a superconductor, usually aluminum, separated by a very thin insulator. And what acts as a nonlinear inductor is Cooper pair channeling across this transition, this superconducting insulator, superconducting transition. So you can write the equations of this element. I will maybe not go into detail, but what's important is that the current through that element scales as the sine of the phase difference, whereas a linear inductor would be directly proportional, where the current is proportional with the inductance L to the phase difference across the junction phi. And if you expand the sign in Taylor to first order, it looks like an inductor, but it has this higher element, which slightly shift the frequency of the higher energy levels. In practice, in order to realize this quantum tunneling element, where you have Cooper pair from one island that can tunnel through, it has obviously to be relatively thin, so that you still have quantum tunneling of Cooper pair across an insulating element. And so what we usually rely on is so-called shadow evaporation of aluminum. That is, we rely on placing a bottom lead of aluminum, letting it oxidize in an atmosphere of oxygen to form a very thin oxide on the order of a nanometer thick, and then place a second layer of this aluminum film on top. And you have an interface that is about 100 nanometer in lateral size, but a nanometer thickness over which the Cooper pair have a high probability of tunneling from one atom to the other. This is one such qubit that we realize in the lab, where you see, obviously in false colors, the capacitive island in red that couples capacitively through the ground plane, which is in gray around it, and also in parallel connecting the ground to the main island are actually two Josephson junction at the tip here of this squid loop. Placing two junction is practical because you can then tune in real time using magnetic flux. Threading through that loop, you can tune the frequency, the resonance frequency of that element, which we will use in order to implement two-qubit gates. Typically, these elements have a resonance frequency on the order of a few gigahertz. It's convenient to work with a few gigahertz because we have a lot of classical electronics that is able to generate pulses, to read out the signals, and in general to operate these devices. And we work, as I said, in this transmon qubit regime. The transmon qubit regime is nice because it's protected from charge noise in the sample. The downside that you pay is that the harmonicity is not big, but is rather limited, on the order of maybe 100 to 300 megahertz. It's also negative, which doesn't matter too much for us, but what it means is that the second transition is slightly less than the first transition of the qubit. This, you might ask, why do we realize something like complicated when you could say trapped a single ion or so and use a real atom that exists? I think there's two reasons. One is we can essentially pick at will the values of our circuit, and not just the values at which the qubit resonates, for example, but also how strongly it couples to any elements around. And we can also fabricate, obviously, where we want, how many we want, using processes that are not unlike CMOS classical fabrication processes. A qubit alone is maybe not sufficient, and you need more things. You need to be able to essentially fulfill DiVincenzo criterion to be able to realize a quantum computer. And so what you need is to be able to control, let it interact with other qubits to do two-qubit gates, as well as read out the state of your qubit. And so we essentially build unit cells where our qubit, which is now this qubit island in yellow, and you don't really see the junction because they're too small at that scale, but they would be here at the tip of this green line, is integrated with more elements. We use the pink line, which is an open-ended coplanar waveguide, to drive voltage pulses and induce Rabi oscillations. So we can use the qubit, which typically is prepared in the ground state by just placing it in a dilution refrigerator at low temperature. And we can send a pulse to prepare an excitation inside the circuit, or even superposition of ground and first excited state. We use the green line, which is a shorted line at the tip, to drive current, and through Ampere's law generate this magnetic flux, which allows to control the operation frequency in real time of this qubit. And what you see around it, this red as well as dark blue resonators are linear resonator that are coupled to the qubit in a dispersive regime, which means that the detuning between the two elements is much bigger than their coupling. And then by probing transmission of a microwave probe tone through this purple feed line, we can infer the state of the qubit. So the response will be different if the qubit is in the ground state than if it was in the excited state. Finally, we want more than one qubit. And so each of those qubits are typically connected to nearest neighbors, up to 4 in our cases, through coupling elements, and the coupling elements are themselves short coplanar waveguide resonators. So if you tile this unit cell over a large scale, then you find something like this, which is a 17-qubit device that we've used to do error correction as well as lattice surgery of repetition code recently, where you see the qubit island in yellow connected to nearest neighbor in this so-called surface code lattice, and each of them routes towards the edge of the chip all the elements that are needed in order to control and read out the circuit. In that case, just to give you an idea of dimension, the scale bar is a millimeter. A chip that contains 17 qubits is about 14 by 14 millimeter in size using our fabrication processes. And the main reason is actually routing signals and also the size of sort of linear control elements. The qubit themselves could be substantially smaller, at least nominally. There's an advantage in lifetime if you make them bigger because you dilute the field and you're less sensitive to losses. But nominally, they could be much smaller and integrated very densely. So we take one of these devices, package it in a setup like this one. This is a recent picture from our lab at PSI, where you see on the front the measurement electronics that generates the pulses, either flux pulses to change the frequency of the qubits, voltage pulses to change the state of the qubit, or probe tone in order to read out the state of the qubits. And on the back is a dilution refrigerator where the sample is installed. And if you take a picture when the dilution refrigerator is open, it looks like these chandeliers where at the top flange you're at room temperature, and as you go down, the temperature goes successively lower until you reach sort of 10 millikelvin, and you have a sample package installed at the very bottom. So this is my recap of how a single quantum processing unit looks like. It's a lattice of nearest neighbor connected, fabricated solid-state artificial atom on which we can control essentially all parameters and perform any quantum operation that are nearest neighbor to qubit gates or single qubit gate or readout in the system. There's, however, increasingly interest into splitting these devices into multiple modules. And maybe I'll come to some of the motivation as we go in this talk. Generally in our lab, what we've realized is that the way you approach connecting different modules will depend strongly on the range of distance that you want to cover. And the range of distance that you want to cover, we separate in long range and short range by essentially comparing to the wavelength of the light, or similarly, you could say comparing to whether it fits in a single cryostat or not. And you can think about building long range couplers and thinking of, for example, sending quantum keys across a quantum network, internet or so. But it's also very interesting of thinking about connecting at a short range small modules, because it's actually hard to scale up your single device to have, let's say, 1,000 fully functional qubits on a single chip. The chip gets big, you have defects in fabrication, and maybe you would prefer to route the signals sort of through carriers at intermediate places or so for input-output, or to even mix technologies and have, let's say, amplifiers integrated close to your qubit, but that are fabricated with different processes, so on different chips. Obviously, we're not the only one working on things like that, and you find works on inter-chip couplings at sort of millimeter scale distance. The one I've put in bold are efforts in our lab that I will tell you a bit in a moment of how they work. And then you can stay in the same cryostat and try to do inter-package communication at sort of maybe 10 centimeters up to a meter distance or so. And at some point, the size of your dilution fridge becomes limiting, and you have to start thinking about how to connect different cryostats on the meter, tens of meter distance is sort of what has been achieved up to now in the literature. Going further is obviously very interesting. I will not talk about it because we don't work actively on it, but the current approach by the community is to think about how to do optical transduction. So to convert microwave energy into optical energy and then send signals through maybe more conventional optical fiber networks that you might already have installed in cities or so. This is all sketched, but it's actually exists as prototypes at sort of all distances that are listed here, where this is a picture from Rigetti, having multiple module and connection that go up and down between module. You can have inside a cryostat sort of 5 packages that are connected and able to generate entanglement. This is from Andrew Cleland. And you can have a cold element over long distance. And this is schematic from our lab, which I would like to cover just right now. I'll tell you a bit of an overview, essentially, of where we stand at the various distances right now. And it's all sort of proof of principle. So it doesn't mean that necessarily what we do couldn't be achieved on a single module. At the moment, I think everything that we do could be achieved on a single module, but we're essentially doing steps in order to prove feasibility before trying later to integrate everything together. And so the first step that I want to describe is essentially the simplest long-range connection that you can do, taking 1 qubit on a single node, single module at one node, and connect it long-range to another qubit that sits far apart. And our motivation was essentially to demonstrate that we can break a loophole-free Bell test, the same that has been also achieved with NV Center, for example, in Delft or so. What we have in order to do that is a quite unique setup where rather than having a single cryostat and everything happening locally, we've connected 2 cryostats, which we call Alice and Bob, or 2 qubits into cryostat, which we call Alice and Bob, through a 30-meter link. And this 30-meter link we've developed in a way that it can remain at millikelvin temperature so that you don't have issues about thermal excitation, creating noise in the microwave band through essentially Maxwell-Boltzmann population. In order to do that, we've costume realized essentially 90-degree rotated fridge where you can recognize, for those who are familiar with cryostat, all the stages that are typically used, an outer vacuum can in which sit 2 stages that are cooled by a pulse tube cooler at 50 Kelvin and 4 Kelvin. And inside are elements that are below liquid helium temperature, where you have a still at about 1 Kelvin, and the base plate temperature is around 20 to 50 millikelvin in this setup, because we have dilution units at the end nodes, but no extra dilution units, so no cooling at the low temperature stages along the full length. Inside this whole setup at cold temperature sits a aluminum waveguide. It's a rectangular WR90 waveguide, and this is where microwave photon that exchange signal in the quantum regime, single photons, from A to B. We always, or nearly always, operated directionally, just from A to B, are propagating with a very low loss. In fact, we've calibrated that loss to be sort of not far from what you would find in an optical fiber. There's about a dB of loss per kilometer, which means that the actual loss that we suffer from are sort of interfaces going from the chip into a cable, going from the cable into the waveguide, and so on, but not so much about the actual distance that we built in this system. As I said, the base plate temperature we managed to keep below 50 millikelvin along the whole 30 meter. And if you come to our lab, which is more like a corridor than a standard lab that you would otherwise see, you would essentially find this long pipe where inside these vacuum cans is all the cooling, as well as the aluminum waveguide where the signal propagates installed. Just to give you an idea about the scale, it's about 14,000 screws that we have to tighten to install the whole thing, so that the two nodes are connected. And then, because this is so long, right, the wavelength of microwave is a few millimeter, and this is propagating over 30 meter here, the signal that we want to send. We essentially send, what we need to send is essentially plane wave, right? This propagating photon in that case, really. Obviously, it's shaped with an envelope, but you would have the photon or the electric field corresponding to that microwave photon to do multiple oscillations. And so what we really want is to convert a stationary excitation inside our qubit into a propagating one, which we can think of really as a microwave photon. And then we have to catch it as it arrives in the second node by performing the reverse operation of the emission. And so this emission, we induce it by connecting our qubit to a so-called transfer resonator. It's in yellow here on the right side. And we actually make use of the fact that our transmon has more than 2 levels. It has a third level, which we typically don't use to do quantum operations, but use here in order to emit microwave photon. So here the levels of the transmon are called G, E, and F. That's ground, first excited, and second excited state. And the 0 and 1, which are behind it, refer to the amount of photon, the Fock state of this transferred cavity. And by driving at the difference frequency, we are able to induce an effective coupling, which we can fully control in amplitude and phase over time between the F0 and the G1 state. And then the G1 state decays very quickly to G0 because the cavity is on purpose lossy. It's connected to the waveguide where the photon propagates, which means by performing local operation, essentially entangling or preparing a superposition of the E and the F state before applying this drive between the F0 and the G1 state, we can essentially first entangle the E and the F state, and then the F state gets converted into a G1, and the G1 releases the photon, which propagates at the speed of light, which means what we end up with is a entangled state between the qubit and a propagating photon. And then on node B, what we do, slightly delayed because we have to wait for the photon to propagate at the speed of light. What we do is the reverse process, and we absorb the incoming photon via the cavity into the F state of the qubit, and then we bring the F population down to the E level or computational subspace in order to do quantum operation, such as, for example, readout and testing whether we violate Bell inequality in the system. This works pretty well. We essentially end up with a Bell state, which of the Bell state you can still pick by doing local rotations. And you can characterize the density matrix. The real one that we found is depicted by this full blue wireframes, and it's compared to both the simulation in red as well as the ideal state in gray. And without going into detail, what you find is a Bell state fidelity of 80%, which is enough to violate the Bell inequality. But, and there's a big but, is like this error is essentially fully dominated by photon loss in the transfer. That is, Alice emitted a photon, but that photon got lost and never got absorbed at the node of Bob. And I have to note that it's not a physical limitation or not a fundamental one. It's just from the way our network is constructed, there's multiple connections, and typically all those connections tend to be a bit lossy, and they sum up along the path. Nevertheless, even if better fidelities have been demonstrated in other labs, if you want to do real large-scale operation, quantum computation with it, you have to sort of be below an error-correcting threshold. And so you need that fidelity to be way higher than what it is currently, which means we have been able to do proof of principle operations like the loophole Fourier Bell test that I mentioned, but also full self-testing of a Bell state, as well as device-independent randomness amplification recently. But we are currently thinking about, is there a way to do quantum error correction on this process, on sending photons from a node A to a node B, despite the fact that some loss will remain, can we do better? And for that, error correction relies on redundancy, which means for redundancy, you need to send more than one photon, more than one qubit of information. And preparing sort of a second link between a second pair of qubit or so would be very costly. And I don't mean just the price, but also just all the instruments and waveguides and everything that you have to place inside. And so what you would rather like is to sort of funnel the quantum information inside a channel that is able to send entangled states that contain multiple effective qubit of information. And we've been working at this. Currently, I have results to show you on the emission side of having a source that is able to generate entangled state of microwave photons. And the source that I would like to present is able to generate time-in entangled states. It's this device on the right, which is niobium on silicon and contains now 2 qubit instead of a single one. It has a so-called emitter qubit. The emitter qubit is connected to an output transmission line, and so it decays relatively fast. It releases its excitations by emitting microwave photon. And it has a storage qubit, if you want, an auxiliary system that is more conventional, like computational, if you want. One of the qubit is interfacing to the waveguide, and one of the qubit is storing information and doing all the standard computations. And now if you consider the first 3 level of the storage qubit and the first 2 level of the other qubit, and the fact that they're coupled via a tunable coupler that allows us to turn the interaction on and off at will, we can actually realize a whole lot of gates between these two systems by driving either the first manifold of excitation between E0 and G1, or driving into second manifold of excitation transition between F0 and E1. This is all driven by sideband transition, essentially, by driving flux through the squeeze loop of the tunable coupler that connects the two elements. And what we showed is that we can do essentially any gate in a generalized family of gate that derive from C0, so partial C0s, as well as swap style of gates. And this is very useful to emit entangled states of photons. States, it turns out, as we started the project, we thought we'll just show the most entangled state that you can do at, let's say, 10 photons or so, a large scale. But it turns out that as you go beyond 3 qubit, even what is the most entangled state is not so clear, because there's different families and different metrics of entanglement, and it all depends on your application. So we asked our collaborators what states are interesting, and they told us, try to realize the cluster state, which is a state that you can do measurement-based quantum computing with. Try to realize the GHZ state, on which you can realize Heisenberg limited metrology as well as quantum teleportation. And why not sending the W state? Because the W state is one where, in principle at least, you can do photon loss resilient quantum communication. And we did that. The protocols that you need to run are pretty straightforward and detailed in this paper, where we actually realized it. And we did that for 2 modes, for 3 modes, for 4 modes. So by modes, I mean photonic bins in this large time bin entangled state. And we found that all the features that you expect are still there for those who recognize density matrices of GHZ states, for example. And the fidelity at which we can do that are at least decent. But going beyond that, it's actually very hard to measure individual microwave photon. So it's actually very hard to reconstruct those density matrices, even despite the fact that our source could go a lot further. And we've operated our source, for example, for some states, I don't recall which one here exactly, up to 15 or even 20 photons. And we saw that at least when you measure power, some photon flux is coming out of the source. And so the question is there still entanglement in that large state? Is it still useful? At which scale is it useful to look at those large states? And it turns out you can essentially find a trick to trace out all the middle part of the state and keep only the first and the last photon in the circuit, and then measure something which is simple, because for 2 qubits, entanglement metrics are well defined, and you can use, for example, negativity, which saturates at 0.5 and then drops towards 0 as the entanglement disappears in your state. And so for all these states, we looked at how does negativity decays versus the site of the state, and we looked at various ways in order to get an estimate of how big the state is that still contains entanglement in the system. I will maybe not go into the details, but what we found is that you can essentially, with this source, generate about 10 entangled photonic modes, which is quite interesting, right? Because the chip on its own physically only contains 2 qubits, but it can emit states that contain beyond 10 entangled photonic qubits in the system. You can not just do frequency multiplexing, but you can essentially scale it up in a second dimension of multiplexing or entanglement, if you want, in the graph, by essentially taking the device that we had before, maybe the lower part, mirror it and copy it on the top part with a second pair of storage qubit, emitter qubit, and send all the photon into the same emission line. And then what you find is 2-dimensionally entangled states, where 1 dimension is the photon arrive at different time, so it's time bin entangled, And the other dimension is actually simultaneously we generate photons at different frequencies, where it's frequency multiplexed, but at the same time. And here again, you sort of find, depending on the metrics that you use, whether you consider only genuinely multipartite entangled state, which is where the fidelity is beyond 50%, you find 8-qubit entanglement. And if you consider non-zero negativity, you can actually push this up to about 16 or so qubits in the system. Maybe I'll stop on the long range here and then move on to the shorter range. As I said, currently on the long range, this multiplexing or this entanglement has only been looked at for us, at least in the emission. And so the good question is, how well does it work once you have loss in the system, in the transfer, and you have to actually absorb and perform essentially error correction or at least error detection on the system? And there's multiple different sort of entangled state that we can actually generate that are essentially linked to a quantum code, an error detection code. And we're currently trying out a few of those and seeing which one has the best trade-off between lower fidelity because the emission complexity is harder, but still maintains the ability to at least error detect or even error correct in the transmission. And this was all effort from our students, postdocs at ETHZ Zurich. And now I will change gear a little bit and talk about short-range modularity, where the principle that we decided to follow is based on three-dimensional integration and placing small chiplets that have a manageable size. The size is good because we know that when we have small sizes, let's say few qubits on the order of 10 or so, we can easily fabricate them in our academic clean room and still have a pretty good yield. We can test at room temperature with the microscope, with the prober, with other tools, whether we think that the device is working before we actually bond it onto a large carrier and connect it to other chiplets. So we can sort of pre-select and then bond the working devices. It could also enable to mix devices or mix fabrication methods, but that's not really something that we follow. And one aspect that has become interesting after we actually started, but we currently also look into, is it may limit error propagation, which is very important when you do error correction to assume that the errors are local and don't propagate from one chip to the other. And that's work from Google, where they actually saw that the cosmic ray could create errors that propagate through the whole sample in superconducting circuits. And so the upgrade that we are doing, let's say, to our fabrication process is to go from a planar device where essentially you have a chip here that is just wire bonded to a PCB and placed in a package into a three-dimensionally integrated device where now you have indium bumps that connect the bottom and the top plane. And you have this extra plane where you can, at the top, have qubits and at the bottom, route signals. And you could place multiple of those on the same carrier. This is a picture of our, let's say, first test that we were doing, verifying that we can have good frequency selectivity or reliability in the targeting, where you have a single module on the carrier. And this is an SCM of the indium bump. Indium is nice because it cold welds, so we can just press the two chips together and they form a direct electrical galvanic contact between the two devices. The issue, because indium is so soft, is you might have tilt when you press. One side might be at a different distance than the other. And because all these circuits are very sensitive on capacitance, you want to control the distance between elements. And so you have to control the tilt by adding spacers. We use resist-based spacers. Those are big squares of SU8 resist of a well-defined thickness. And so they act as stop. When we press until we reach the spacer, and then stop at a 10 micron distance. So this is obviously not to scale. The distance between the two chips is typically 10 micron, but the size of a chip is maybe 10 millimeter or so. Here we started by essentially placing 4 modules of 1 qubit each and connecting the module pairwise. So the top 2 modules are connected, bottom 2 modules are connected, but we skipped the vertical connections in between the two. We realized qubits were these pictures you have to look at as the red part is what happens on the top chip, and the blue part is what happens on the bottom chip. And so you have a qubit island on the top chip here in red with its own flex line and coupler to the neighboring qubit. And both the flex line and the coupler are routed via indium bumps, the green dots, into the carrier part of the signal routing of the coupler, and then back up onto the other chip to a qubit of another module. You also have readout resonator and charge line, but those are routed conventionally on a single chip and rely on across the spacing capacitance between the two chips. This is a picture, for example, of the bottom chip right before you bond both chips together. And so now you don't see the qubit because it would be on the top chip only. And what we demonstrate in this manuscript that just got accepted is that we can essentially do operation at a similar level of fidelity than we can do on a single chip with sort of 98% single shot readout, 10 to the minus 3 single qubit error, and 10 to the minus 2 two-qubit gate errors. And at this point, our question was, there's only 1 qubit on the module, and so we characterize the gate across modules, but how well does that compare to gates that are inside the module? And so we tried to realize 2 by 3 qubit, let's say small network. And what's nice compared to the long range connection is that we can actually have the carrier have really all-to-all sort of, or at least pairwise, but dense couplers, and we don't have to multiplex through a single channel. And so Kieran Dalton, our PhD student, realized this device, which you see as a sketch up here and as a real picture down there before we mounted it in the fridge, which has 3 qubits on each device, a coupler within the module, as well as across the module, which are routed through the carrier. And essentially, we can't distinguish the performance in the 2-qubit gate, whether it routes through the module or not, through the carrier or not, doesn't really affect the result. At this point, we started to think about other algorithms that benefit from being distributed across 2 samples. And the answer is yes, there are algorithms such as cross-platform verification. Cross-platform verification is essentially asking, once my quantum computer is big enough that I can trust its result by simulating it classically, but I really have to find another way of verifying that it does the right thing. What can I do? I can take a second quantum computer and compare the results. And compare the results, for example, on a relatively easy task here, preparing a GHZ state. Comparing the result could mean doing full quantum state tomography, or using clever tricks such as comparing pairwise all the qubits of the system, qubit 1 of computer 1 to qubit 1 of computer 2, etc., etc. And this is called Bell basis measurement. There's a rule of how you have to compare the results. It uses quantum gates, so you have to perform more operation than actually just prepare the 2 states. But what we show in this paper here, and was predicted experimentally as a protocol, is that it's actually more efficient. As you may know, quantum state tomography requires exponential repetition of the states, whereas cross-platform verification via Bell basis measurement doesn't. It can be more efficient in the term of how many times you have to repeat the operation to have a certain certainty that the 2 states are the same. Maybe I will not go through a whole lot of detail about what the results are. What we looked at is first, as a function of the rotation angle on one of the states, how close are the two states. So what we measure is actually the inner product of the two states of the two computers. And at 0 or at 2 pi phase, they're the same. And then as we rotate the phase, they get orthogonal. And so the inner product dropped to 0. And we verify that both with quantum state tomography as well as with Bell basis measurement. And you see that with Bell basis measurement, the agreement is slightly worse, especially as we increase the number of qubits in the system. And that's because we have to add all these 2-qubit gate in order to compare the two states. But what's interesting is if you consider how many repetition of the experiment do you need to have a certain variance, a certain confidence in that the two results, or in that your inner product has converged to the correct value. And that scales exponentially if you do quantum state tomography for 1, 2, and 3 qubits. Whereas, and even if you do clever randomized measurement rather than full quantum state tomography or so, it still scales exponentially. And there's a little better offset, but it still scales exponentially. Whereas as you use your quantum connection between the different modules, then suddenly this trend flattens out. And nominally it should be flat. In our case, it still scales up a little bit. And that's because we have reduced fidelity. And then when you have reduced fidelity, you have a reduced trial success probability through Bernoulli law of probabilities. And so we verified also in simulations numerically that if you were to reduce the error substantially, then essentially the number of repetition is flat, and you can gain orders of magnitude in the speed at which you reach your confidence that the two results are the same. So now essentially we're thinking about let's bring two computers together, but do something more interesting than just compare the results. And what you often find is that if you have two computers connected, it might be that one of the computers is much better than the other. And so you end up in a sort of client-server situation where you have someone with a big computer, high level of resources that can send quantum states to someone else, a client that has a lower level of resources, but maybe is able to, with an FPGA in real time, essentially learn about his own states and then ask for more resources from the server. And that could be measurement-based quantum computing. That could also be essentially trying to distribute your own task, if you're a client, to not send it to a single quantum server, but to try to distribute it across multiple servers where you might not trust, for example, that one of the server keeps the privacy of your setup, but if you distribute across multiple ones, that could be the case. And so the final step that's missing for us is essentially to connect a computer with an FPGA and then to, in real time, while you store the result, or while the quantum state is still alive, let's say, interpret the result and then do some operation on the control. And we've essentially made an experiment that tries to look at this by implementing mean-secret measurement as well as feed-forward. And the experiment realizes a so-called quantum fan-out gate. I think in the interest of time, I will not describe the fan-out in too much detail, but just to give you an idea of how it works in practice, you have your classical device. In our case, it's Zurich instruments devices that can generate or that can acquire readout signal and that can drive qubits. And you might have multiple of those because each of those can operate only 6 qubits. What we've placed is a system controller, and the system controller can sort of acquire all the measurement result from all the separate readout results, and then currently look up through a table, but it could also run a simple algorithm on an FPGA and decide on which of the qubit need to be rotated or read out in the next step, and then send those commands again to the individual qubit controller in order to know which next steps to take. Typical delay is about 600 nanoseconds, which is actually much faster than the sort of 50 to 100 microsecond lifetime of the qubits that we use in our system. Let me skip the result. We just realized this fan-out gate, and if you are interested, it actually works, and you can read it out in our PhysRev applied reference by our PhD student, Yongxing Song. I will not go into detail about how well that works, and rather leave a bit of time for question. So in summary, what we envision really is the ability in superconducting circuits to build a large-scale network that has short-range connection that improve the yield, that has long-range connection that can connect remote devices, and on which you can, in real time, read out the result and adjust your operation so that you can really distribute application across the full network. This is a combination of many years of work in quantum optics on the left rather, and in 3D integration and feed-forward work that you find references on the right. And it's obviously many, many people at ETH and at PSI that help us, from PhD student, postdoc, technical staff, engineers. And you find a picture of our last brainstorm that we just had to define the goal of our next year here. So I thank you very much for your attention, and I would be happy to take questions.
Thank you very much, Jean-Claude, for the very beautiful and interesting talk. Any questions? Oh, yes. Any questions from the audience, from the participants?
Yeah, thank you very much, Jean-Claude, for this very nice introduction to the transmon technology and also to the modularity of these systems, right? So short range and long range. So I have a question about, I think it was in slide 10, when you showed the fidelity that you achieve after the transmission of the, qubit. I'm not mistaken. And you compare also with your simulation. So you say there, if I'm not wrong, that the main, let's say, parameter or effect that affects it is the photon loss, right?
Right.
And I think you compare the real experiment with a simulation. So you have any model to characterize, that characterize that experiment that you can simulate? I mean, like includes this photon loss and other parameters to take into account, for instance, how well the entanglement between the qubit and the photon is, and so, or the delay, how that affects, right? So, yeah, I would like to see, long story short, so is there any model or any analytical model you use, or what kind of simulation environment you use to compare, let's say, the real experiment with the simulated one?
Yeah, that's correct. So this is actually all work that you would find in this Nature paper. That's work that's done together with our theory partner at Sherbrooke. What they do is essentially master equation simulation of the full system. And what we input is essentially parameters that we get from separate calibration experiments. So we, for example, measure T1 and T2 of our qubit and provide that as an input, and they use it to know, given the length of our pulse, for example, that we apply, how much of the energy decay will occur and will not be emitted as a photon, but rather be lost because of T1 and finite lifetime of a qubit. Mm-hmm. And we also do experiments where we actually just do not send a photon from A to B, let's say. Here, we send from Alice to Bob, but we also do experiment where we just emit the photon at Alice and then try to collect it with a linear amplifier. And then we characterize, for example, how good was the emission. And what we do also is emit from Alice and not catch at Bob, but let it reflect. And then absorb at Alice back again. We call that a ping pong. Alice emits, the photon propagates away and then comes back, and we try to absorb it. And then from having done essentially 2 paths through the link, we can get some information about the loss in the propagation. And so we have a set of calibration experiment from which we extract parameters. And those parameters go into a master equation simulation that predict the density matrix.
Okay. Yeah, thank you very much.
Thank you. There is a question from Peter.
So thank you for the really wonderful presentation. Yeah, and so I'm a microwave engineer, part of the QUADRATURE project. And I'm interested basically in both the long ranges as well as the short range. For the long range, so we do here also some superconducting hollow waveguides. What are the predominant mechanisms why you lose your photon in this kind of environment? Is it the length, the temperature, would you gain if you would get a superconducting hollow waveguide for this transfer?
It's a very good question, and it's something that our understanding has evolved over the years. It is, just to confirm, it is actually a superconducting hollow waveguide. Maybe it's not so clear in the picture, but it is a superconducting aluminum hollow waveguide. Our current understanding is most of the loss is actually not real loss, but is actually impedance matching loss, let's say. Okay. You have to go from the chip into this waveguide. And you have to realize when you cool down a 30-meter long link, it will thermally contract by about 15 centimeters. So you can't just leave a waveguide directly at the chip because something has to take the slack and the waveguide is very rigid. And so what we connect in between the chip and the waveguide is sort of a little bit of a looped cable that can then sort of contract and expand as the system cools down. We have to go essentially from a photon in a coplanar waveguide on the chip through wire bond to a PCB, through a connector inside that cable, and then into a cable to waveguide adapter, and then the photon propagates in the waveguide. And interestingly, what we found is that we did this system at 5 meter and at 30 meter, and the fidelity is essentially exactly the same. So it's not length. It's really interfaces. Which one of the interfaces is still something we're working on. Okay.
Well, fascinating. Yeah, we're working on a similar direction with a bit higher TC titanium nitride as a superconductor. Okay. And that's what is fascinating for us.
Yeah, no, it's very interesting.
Yeah, in the near field, the chiplet integration case, there your results were spectacular. Yeah, that basically you attain almost the same fidelity for the intra-chip or the inter-chip type of transfer. What kind of, which means that basically the losses of your transition are negligible and impedance matching from going up and down.
That's correct.
Are your losses on the classical chip so bad, or how did you manage to get this to so low values?
I think what you have to realize is once your distance is less than the wavelength or so, you can't really think about a plane wave coming in and get reflected, but it's more like if you have an impedance mismatch in the transition, what will happen is you renormalize the line width. So you have a slightly less coupling, your gate is slightly slower, but we can compensate for that by essentially increasing the capacitive connection to the qubit itself.
Then you compensate, and then at the end you are, okay, good.
Exactly.
Then I get it. Okay, yeah.
Exactly. I hope that was clear. But essentially, we compensate by making this coupler a bit wider, a bit bigger, this capacitance a bit bigger. We compensate for the fact that this impedance mismatch, which is close by, reduces the line width a little bit.
Okay. No, thank you. And thank you for your openness. Yeah, this is fascinating for us, and it's really remarkable. Thank you very much.
Very happy. Thanks.
Good. Any other questions from the audience? Yeah. Yes, Carmina.
if nobody else wants to want a question, I will take this opportunity to ask another one. So I know that your group has been also very active in quantum error correction, modeling surface code, right? And you have demonstrated this logical error rate. Yeah. So I was wondering in this tilted architecture, right? The thing that you go this modular is because you want to go larger and to include quantum error correction, right? So you didn't discuss that in this talk, but any thoughts of the integration of quantum error correction, in your case, I guess, surface code in this modular architecture? So in other words, so how to distribute the logical qubits, the operations between them, although it seems that this short range, let's say, link it's comparable to the intra link. So any thoughts here?
Yeah, that's a very good question. I can't give you a definitive answer because we don't have it yet. But it's I think when you do things locally, it's very likely that because we can essentially put as many couplers as we want on the carrier chip, it's very likely that if you would do let's say a 1,000 qubit surface code, everything local, which is something that's realistic, I would say. It's maybe a big effort for us, but for a company like Google or IBM, you could do that. You would not see currently a reason to go to something else than a surface code and just pack many couplers in the carrier and keep using what you know how to use well. Where I find more interesting conceptually is at the long distance, you wouldn't do that because it's just you wouldn't do that many links. And also, if you think about internet going from your home to a server somewhere, you don't have the internet server of a classical company provider or so sending a single optical fiber to every home at the next city, but you have to route things cleverly in a bigger network. And it turns out once you route things cleverly, the optimal error correction codes are different because the surface code works in a regime where you assume all errors are roughly equal. That's where it's great because you get a high threshold and you can correct for those all errors equally. But then you suddenly start having a very biased noise error model, right? The main error that you should care about is photon loss and not so much anything else. You could run locally surface codes to correct for all other errors on your single node. And the main error that you remain and that you have to care about is the loss in the propagation. And once you have a single error that dominates everything else, it's a bit like this cat qubits, if you heard about, or other codes. Suddenly something else than the surface code might be way better, way more efficient in terms of overheads. And here we haven't really explored much yet, so I can't say, but I would be very surprised if people would use a surface code in a communication setting or so.
Okay, thank you very much.
So if there are no other questions, we can conclude this second webinar. And thank you again, Jean-Claude. And
thank you.
I invite all the audience to follow the LinkedIn page of QUADRATURE to keep posted with initiatives and next webinars. And as mentioned at the beginning of this webinar, this seminar is recorded and will be available in the QUADRATURE YouTube channel soon. So thank you very much again, and I hope to see you all soon for the next webinars.